The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so I'd like to begin the second lecture by reminding you what we did last time. So last time, we defined the derivative as a slope of a tangent line. So that was our geometric point of view. And we also did a couple of computations. We worked out that the derivative of 1 over x was minus 1 over x squared. And we also computed the derivative of x to the nth power for n equals 1, 2, etc. And that turned out to be nx to the n minus 1. So that's what we did last time. And today, I want to finish up with other points of view on what a derivative is. So this is extremely important. It's almost the most important thing I'll be saying in the class, but you'll have to think about it again when you start over and start using calculus in the real world. So again, we're talking about what is a derivative. And this is just a continuation of last time. So as I said last time, we talked about geometric interpretations. And today, what we're going to talk about is rate of change as an interpretation of the derivative. So remember, we drew graphs of functions, y equals f of x, and we kept track of the change in x, and here the change in y, let's say. And then, from this new point of view, a rate of change, keeping track of the rate of change of x and the rate of change of y, it's the relative rate of change we're interested in, and that's delta y over delta x. And that has another interpretation. This is the average change. Now, usually, we would think of that if x were measuring time, and so the average, and that's when this becomes a rate. And the average is over the time interval delta x. And then the limiting value is denoted dy dx. And that is so this one is the average rate of change, and this one is the instantaneous rate. Okay, so that's the point of view that I'd like to discuss now and give you just a couple of examples. So let's see. Well, first of all, so maybe some examples from physics here. So Q is usually the name for a charge. And then dq dt is what's known as current. So that's one physical example. A second example, which is probably the most tangible one, is we could denote the letter S by distance. And then the rate of change is what we call speed. So those are the two typical examples, and I want to illustrate the second example in a little bit more detail, because I think it's important to have some visceral sense of this notion of instantaneous speed. And I get to use the example of this very building to do that. Probably you know, or maybe you don't, that on Halloween there's an event that takes place in this building, or really from the top of this building, which is called the pumpkin drop. So let's illustrate this idea of rate of change with the pumpkin drop. So what happens is this building, well, let's see, here's the building. And here's the dot. That's the beautiful grass out on this side of the building, okay? And then there's some people up here and very small objects. Well, they're not that small when you're close to them, that get dumped over the side there, and they fall down. That's, you know, everything at MIT, or a lot of things at MIT, are physics experiments. So that's the pumpkin drop. So roughly speaking, actually, the building's about 300 feet high. We're down here on the first usable floor, and so we're going to use, instead of 300 feet, just for convenience purposes, we'll use 80 meters, because that makes the numbers come out simply. Okay, so we have the height, which starts out at 80 meters at time 0, and then the acceleration due to gravity gives you this formula for h. This is the height. So at time t equals 0, we're up at the top. H is 80 meters. So this is the units here are meters. And at time t equals 4, you notice 5 times 4 squared is 80. So I picked these numbers conveniently so that we're down at the bottom. Okay, so this notion of average change here, so the average change, or the average speed here, maybe we'll call it the average speed, since that's over this time that it takes for the pumpkin to drop, is going to be the change in h divided by the change in t, which is, it starts out at, what does it start out as? It starts out as 80, right? And it ends at 0. So actually, we have to do it backwards. We have to take 0 minus 80, because the first value is the final position, and the second value is the initial position. And that's divided by 4 minus 0, time 4 seconds minus time 0 seconds. And so that, of course, is minus 20 meters per second. So the average speed of this guy is 20 meters a second. Now, so why did I pick this example? Because, of course, the average, although interesting, is not really what anybody cares about who actually goes to the event. All we really care about is the instantaneous speed when it hits the pavement. And so that can be calculated at the bottom. So what's the instantaneous speed? That's the derivative. Or maybe I should, to be consistent with the notation I've been using so far, that's d by dt of h. All right? So that's d by dt of h. Now remember, we have formulas for these things. We can differentiate this function now. We did that yesterday. So we're going to take the rate of change, and if you take a look at it, it's just the rate of change of 80 is 0 minus the rate of change for this minus 5t squared. That's minus 10t. All right? So that's using the fact that d by dt of 80 is equal to 0, and d by dt of t squared is equal to 2t. The special case, well, I'm cheating here, but there's a special case that's obvious. I didn't throw it in over here. The case n equals 2 is that second case there, but the case n equals 0 also works, right? Because that's constants. The derivative of a constant is 0, and then the factor n there is 0, and that's consistent. And actually, if you look at the formula above it, you'll see that it's the case n equals minus 1. So we'll get a larger pattern soon enough with the powers. OK, anyway, back over here, we have our rate of change. And this is what it is. And at the bottom, at the point of impact, we have t is equal to 4. And so h prime, which is the derivative, is equal to minus 40 meters per second. So twice as fast as the average speed here. And if you need to convert that, that's about 90 miles an hour, which is why the police are there at midnight on Halloween to make sure you're all safe, and also why when you come, you have to be prepared to clean up afterwards. So anyway, that's what happens. It's 90 miles an hour. It's actually, the building's a little taller, but there's air resistance, and I'm sure you can do a much more thorough study of this example. All right, so now I want to give you a couple of more examples, because time is, and these kinds of parameters and variables are not the only ones that are important for calculus. If it were only this kind of physics that was involved, then this would be a much more specialized subject than it is. And so I want to give you a couple of examples that don't involve time as a variable. So the third example I'll give here is the letter T often denotes temperature. And then dt dx would be what is known as the temperature gradient, which we really care about a lot when we're predicting the weather, because it's that temperature difference that causes airflows and it causes things to change. And then there's another theme which is throughout the sciences and engineering, which I'm going to talk about under the heading of sensitivity of measurements. So let me explain this. I don't want to belabor it, because I just am doing this in order to introduce you to the ideas on your problem set, which are the first case of this. So on problem set 1, you have an example which is based on a simplified model of GPS, sort of the flat Earth model. And in that situation, well, if the Earth is flat, it's just a horizontal line like this. And then you have a satellite, which is over here, preferably above the Earth. And the satellite knows exactly, or the system knows exactly where the point directly below the satellite is. So this point is treated as known. And I'm sitting here, okay, with my little GPS device. And I want to know where I am. And the way I locate where I am is I communicate with this satellite by radio signals. And I can measure this distance here, which is called h. And then the system will compute this horizontal distance, which is L. So in other words, what's measured, so h measured by radio waves and a clock, or various clocks. And then L is deduced from H. And what's critical in all of these systems is that you don't know H exactly. There's an error in H, which will denote delta H. There's some degree of uncertainty. The main uncertainty in GPS is from the ionosphere, but there are lots of corrections that are made of all kinds. And also, if you're inside a building, it's a problem to measure it. But it's an extremely important issue, as I'll explain in a second. So the idea is we then get to the get at delta L is estimated by considering this ratio, delta L over delta H, which is going to be approximately the same as the derivative of L with respect to H. So this is the thing that's easy because, of course, it's calculus, right? Calculus is the easy part, and that allows us to deduce something about the real world that's close by over here. So the reason why you should care about this quite a bit is that it's used all the time to land airplanes. And so you really do care that they actually know to within a few feet or even closer where your plane is and how high up it is and so forth. All right. So that's it for the general introduction to what a derivative is. I'm sure you'll be getting used to this in a lot of different contexts throughout the course. And now we have to get back down to some rigorous details. Okay? Is everybody happy with what we've got so far? Yeah?
How did you get the equation for height?
Good question. The question was, how did I get this equation for height? I just made it up because it's the formula from physics that you will learn when you take 801. And it has to do with the fact that in fact, it has to do with the fact that this is speed, if you differentiate another time, you get acceleration. And this is the acceleration due to gravity is 10 meters per second, which happens to be the second derivative of this. But anyway, I just pulled it out of a hat from your physics class. So you can just say C801. All right. Other questions? All right, so let's go on now. Now, I have to be a little bit more systematic about limits. And so let's do that now. So now what I'd like to talk about is limits and continuity. And this is a warm-up for deriving all the rest of the formulas, that I'm going to need to differentiate every function you know. Remember, that's our goal, and we only have about a week left, so we'd better get started. So first of all, there's what I will call easy limits. So what's an easy limit? An easy limit is something like the limit as x goes to 4 of x plus 3 over x squared plus 1. And with this kind of limit, all I have to do to evaluate it is to plug in x equals 4. Because, so what I get here is 4 plus 3 divided by 4 squared plus 1. And that's just 7 divided by 17. And that's the end of it. So those are the easy limits. The second kind of limit, well, so this isn't the only second kind of limit, but I just want to point this out. It's very important, is that derivatives are always harder than this. You can't get away with nothing here. So why is that? Well, when you take a derivative, you're taking the limit as x goes to x0 of f of x, well, f of x, let's try. Yeah, we'll write it all out in all its glory. Here's the formula for a derivative. Now notice that if you plug in x equals x0, always gives 0 over 0. So it just basically never works. So we always are going to need some cancellation. To make sense out of the limit. Now, in order to make things a little easier for myself to explain what's going on with limits, I need to introduce just one more piece of notation. What I'm going to introduce here is what's known as a left-hand and a right-hand limit. If I take the limit as x tends to x0 with a plus sign here of some function, this is what's known as the right-hand limit. And I can display it visually. So what does this mean? It means practically the same thing as x tends to x0, except there's one more restriction which has to do with this plus sign, which is we're going from the plus side of x0. That means x is bigger than x0. And I say right hand, so there should be a hyphen here, right hand limit, because on the number line, if x0 is over here, the x is the x is to the right. All right, so that's a right-hand limit. And then this being the left side of the board, I'll put on the right side of the board the left limit, just to make things confusing. So that one has the minus sign here. I'm just a little dyslexic, and I hope you're not. So I may have gotten that wrong, but okay. So this is the left-hand limit. And I'll draw, so of course that just means x goes to x0, but x is to the left of x0. And again, on the number line, here's the x0, and the x is on the other side of it. Okay, so those two notations are going to help us to clarify a bunch of things. It's much more convenient to have this extra bit of description of limits than to just consider limits from both sides. Okay, so I want to give an example of this. And also an example of how you're going to think about these sorts of problems. So I'll take a function which has two different definitions. Say it's x plus 1 when x is bigger than 0, and minus x plus 2 when x is less than 0. All right, so maybe put commas there. Those are, so when x is greater than 0, it's x plus 1. Now, I can draw a picture of this. It's going to be kind of a little small, because I'm going to try to fit it down in here, but maybe I'll put the axis down below. So at height 1, I have, to the right, I have something of slope 1. So it goes up like this. All right? And then to the left of 0, I have something which has slope negative 1. But it hits the axis at 2, so it's up here. All right? So I have this sort of strange antenna figure here, which is my graph. Maybe I should draw these in another color to depict that. All right? And then if I calculate these two limits here, what I see is that the limit as x goes to 0 from above of f of x, that's the same as the limit as x goes to 0 of the formula here, x plus 1, which turns out to be 1. And if I take the limit from the, so that's the left-hand limit, that's this, yeah, I told you I was dyslexic. Which, right, this is the right. So it's that right half. Here we go. So now I'm going from the left, and it's f of x again. But now, because I'm on that side, the thing I need to plug in is the other formula, minus x plus 2. And that's going to give us 2. Now, notice that the left and right limits, and this is one little tiny subtlety, and it's almost the only thing that I need you to really pay attention to a little bit right now, is that this, we did not need x equals 0 value. In fact, I never even told you what f of 0 was here. If we stick it in, we could stick it in, okay, let's say we stick it in on this side. Let's make it be that it's on this side. So that means that this point is in, and this point is out. So that's a typical notation, this little open circle and this closed dot for when you include the, so in that case, the value of f of x happens to be the same as its right-hand limit, namely the value is 1 here, and not 2. Okay, so that's the first kind of example. Questions? Okay, so now our next job is to introduce the definition of continuity. So that was the other topic here. So we're going to define, so f is continuous at x0 means that the limit of f of x as x tends to x0 is equal to f of x0. Right? So the reason why I spent all this time paying attention to the left and the right and so on and so forth and focusing is that I want you to pay attention for one moment to what the content of this definition is. What it's saying is the following. So continuous at x0 has various ingredients here. So the first one is that this limit exists. And what that means is that there's an honest limiting value both from the left and right. And they also have to be the same. All right, so that's what's going on here. And the second property is that f of x0 is defined. So I can't be in one of these situations where I haven't even specified what f of x0 is, and they're equal. Okay? So that's the situation. Now, again, let me emphasize a tricky part of the definition of a limit. This side, the left-hand side, is completely independent, is evaluated by a procedure which does not involve the right-hand side. These are separate things. This one is, to evaluate it, you always avoid the limit point. So that's, if you like, a paradox, because it's exactly the question is it true that if you plug in x0, you get the same answer as if you move in the limit? That's the issue that we're considering here. We have to make that distinction in order to say that these are two, otherwise this is just tautological. it's a very little, it doesn't have any meaning. But in fact, it does have a meaning because one thing is evaluated separately with reference to all the other points, and the other is evaluated right at the point in question. And indeed, what these things are exactly the easy limits. That's exactly what we're talking about here. They're the ones that you can evaluate this way. So we have to make the distinction, and these other ones are going to be the ones which we can't evaluate that way. So these are the nice ones, and that's why we care about them, why we have a whole definition associated with them. All right. So now what's next? Well, I need to give you a little tour, a very brief tour of the zoo of what are known as discontinuous functions. So sort of everything else that's not continuous. So the first example here, let me just write it down here, is jump discontinuities. So what would a jump discontinuity be? Well, we've actually already seen it. The jump discontinuity is the example that we had right there. This is when the limit from the left and right exist but are not equal. Okay, so that's as in the example. Right, in this example, the two limits, one of them was 1 and one of them was 2. So that's a jump discontinuity. And this kind of issue of whether something is continuous or not is may seem a little bit technical, but it is true that that people have worried about it a lot. Bob Merton, who was a professor at MIT when he did his work for the Nobel Prize in economics, was interested in this very issue of whether stock prices of various kinds are continuous from the left or right in a certain model. And that was a very serious issue in developing the model that priced things that our hedge funds use all the time now. So left and right really can mean something very different. In this case, left is the past and right is the future. And it makes a big difference whether things are continuous from the left or continuous from the right. Right? Is it true that the point is here, somewhere in the middle, somewhere else? That's a serious issue. So the next example that I want to give you is a little bit more subtle. It's what's known as a removable discontinuity. And so what this means is that the limit from left and right are equal. So a picture of that would be you have a function which is coming along like this, and there's a hole maybe where, who knows, either the function is undefined or maybe it's defined up here, and then it just continues on. All right, so the two limits are the same. And then, of course, the function is begging to be redefined so that we remove that hole, and that's why it's called a removable discontinuity. Now let me give you an example of this, or actually a couple of examples. So these are quite important examples which we'll be working with in just a few minutes. So the first is the function g of x, which is sine x over x, and the second will be the function h of x, which is 1 minus cosine x over x. So we have a problem at g of 0 is undefined. On the other hand, it turns out that this function has what's called a removable singularity, namely the limit as x goes to 0 of sine x over x does exist. In fact, it's equal to 1. So that's a very important limit that we'll work out either at the end of this lecture or the beginning of next lecture. And similarly, the limit of 1 minus cosine x divided by x goes to 0, is 0. All right, maybe I'll put that a little farther away so you can read it. Okay, so these are very useful facts that we're going to need later on. And what they say is that these things have removable singularities. Sorry, removable discontinuity at x equals 0. All right, so as I say, we'll get to that in a few minutes. Okay, so are there any questions before I move on? Yeah. The question is, why is this true? Is that what your question is? And the answer is, it's very, very unobvious. I haven't shown it to you yet. And if you were not surprised by it, then that would be very strange indeed. So we haven't done it yet. You have to stay tuned until we do. Okay? We haven't shown it yet. And actually, even this other statement, which maybe seems stranger still, is also not yet explained. Okay? So we are going to get there, as I said, either at the end of this lecture or at the beginning of next. Other questions? All right, so let me just continue my tour of the zoo of discontinuities. And I guess I want to illustrate something with the convenience of right and left-hand limits. So I'll save this board about right and left-hand limits. So a third type of discontinuity is what's known as an infinite discontinuity. And we've already encountered one of these. I'm going to draw them over here. Remember, the function y is 1 over x. That's this function here. But now I'd like to draw also the other branch of the hyperbola down here and allow myself to consider negative values of x. So here's the graph of 1 over x. And the convenience here of the distinguishing the left and the right-hand limits is very important, because here I can write down that the limit as x goes to 0 plus of 1 over x. Well, that's coming from the right, and it's going up. So this limit is infinity, whereas the limit in the other direction from the left, that one is going down. And so it's quite different. It's minus infinity. Now, some people say that these limits are undefined, but actually they're going in some very definite direction. So you should, whenever possible, specify what these limits are. On the other hand, the statement that the limit as x goes to 0 of 1 over x is infinity is simply wrong. Okay? It's not that people don't write this. It's just that it's wrong. It's not that they don't write it down. I mean, in fact, you'll probably see it. And it's because people are just thinking of the right-hand branch. It's not that they're making a mistake necessarily, but anyway, it's sloppy. And there's some sloppiness that will endure and others that will try to avoid. So here you want to say this, and it does make a difference. Plus infinity is an infinite number of dollars, and minus infinity is an infinite amount of debt. They're actually different. They're not the same. So, this is sloppy, and this is actually more correct. Okay, so now in addition, I just want to point out one more thing. Remember, we calculated the derivative, and that was minus 1 over x squared. But I want to draw the graph of that and make a few comments about it. So I'm going to draw the graph directly underneath the graph of the function. And notice what this graph is. It goes like this. It's always negative, and it points down. So now this may look a little strange that the derivative of this thing is this guy. But that's because of something very important, and you should always remember this about derivatives. The derivative of a function looks nothing like the function necessarily. So you should just forget about that as being an idea. Some people feel like if one thing goes down, the other thing has to go down. Just forget that intuition. It's wrong. What we're dealing with here, if you remember, is the slope. So if you have a slope here, that corresponds to just a place over here. And as the slope gets a little bit less steep, that's why we're approaching the horizontal axis. We're getting the number's getting a little smaller as we close in. Now over here, the slope is also negative. It's going down. And as we get down here, it's getting more and more negative. As we go here, the slope, this function is going up, but its slope is going down. All right, so the slope is down on both sides. And the notation that we use for that is well suited to this left and right business. Namely, the limit as x goes to 0 of negative 1 over x squared, that's going to be equal to minus infinity. And that applies to x going to 0 plus and x going to 0 minus. So both have this property. And finally, let me just make one last comment about these two graphs. This function here is an odd function. And when you take the derivative of an odd function, you always get an even function. And that's closely related to the fact that this 1 over x is an odd power and this 2, x to the first power is an odd power and x squared is an even power. So all of your intuition should be reinforcing the fact that these pictures look right. Okay, now there's one last kind of discontinuity that I want to mention briefly, which I will call other. Ugly discontinuities. And there are lots and lots of them. And so one example would be the function y is equal to sine 1 over x as x goes to 0. And that looks a little bit like this. Back and forth and back and forth. It oscillates infinitely often as we tend to 0. And there's no left or right limit in this case. So there is a very large quantity of things like that. Fortunately, we're not going to deal with them in this course. A lot of times in real life, there are things that oscillate as time goes to infinity, but we're not going to worry about that right now. Okay, so that's our final mention of a discontinuity. And now I need to do just one more piece of groundwork for our formulas next time. Namely, I want to check for you one basic fact, one limiting tool. So this is going to be a theorem, but fortunately it's a very short theorem and it has a very short proof. So the theorem goes under the name differentiable implies continuous. And what it says is the following. It says that if f is differentiable, in other words, the derivative exists at x0, then f is continuous at x0. So we're going to need this as a tool, a key step in the product and quotient rules. So I'd like to prove it right now for you. So here's the proof. Fortunately, the proof is just one line. So first of all, I want to write in just the right way what it is that we have to check. So what we have to check is that the limit as x goes to x0 of f of x minus f of x0 is equal to 0. So this is what we want to know. We don't know it yet, but we're trying to check whether this is true or not. So that's the same as the statement that the function is continuous, because the limit of f of x is supposed to be f of x0. And so this difference should have limit 0. And now, the way this is proved is just by rewriting it by multiplying and dividing by x minus x0. So I'll rewrite the limit as x goes to x0 of f of x minus f of x0 divided by x minus x0 times x minus x0. Okay, so I wrote down the same expression that I had here. This is just the same limit, but I multiplied and divided by x minus x0. And now, when I take the limit, what happens is the limit of the first factor is f prime of x0. That's the thing we know exists by our assumption. And the limit of the second factor is 0, because the limit is x goes to x0 of x minus x0 is clearly 0. So that's it. The answer is 0, which is what we wanted. All right, so that's the proof. Now, there's something exceedingly fishy looking about this proof. And let me just point to it before we proceed. Namely, you're used in limits to setting x equal to 0. And this looks like we're multiplying and dividing by 0, exactly the thing which makes all proofs wrong in all kinds of algebraic situations and so on and so forth. You've been taught that that never works, right? But somehow these limiting tricks have found a way around this. And let me just make explicit what it is. In this limit, we never are using x equals x0. That's exactly the one value of x that we don't consider in this limit. That's how limits are cooked up. And that's sort of been the theme so far today, is that we don't have to consider that. And so this multiplication and division by this number is legal. It may be small, this number, but it's always non-zero. And so this really works, and it's really true, and we've just checked that a differentiable function is continuous. So I'm going to have to do these, carry out these limits, which are very interesting 0 over 0 limits next time. But let's hang on for 1 second to see if there are any questions before we stop. Yeah, there is a question.
Can you go for the proof right there, please?
Repeat this proof right here.
Minus x0 and the y
Okay. Just say again.
Originally it's x minus x0. And put it at the bottom. Y multiplied.
Okay, so there are two steps to the proof, and the step that you're asking about is the first step, right? And what I'm saying is if you have a number and you multiply it by 10 over 10, it's the same number. If you multiply it by 3 over 3, it's the same number, 2 over 2, 1 over 1, and so on. So it's okay to change this to this. It's exactly the same thing. That's the first step. Yes? The question was, how does this line, yeah, where the question mark is. So what I checked was that this number, which is on the left-hand side, is equal to this very long, complicated number, which is equal to this number, which is equal to this number. And so I've checked that this number is equal to 0 because the last thing is 0. This is equal to that, is equal to that, is equal to 0. And that's the proof. Yes? Yeah. So that's a different question. Okay. So the hypothesis of differentiability I use because this limit is equal to this number, that limit exists. That's how I use the hypothesis of the theorem. The conclusion of the theorem is the same as this because being continuous is the same as limit as x goes to x0 of f of x is equal to f of x0. That's the definition of continuity. And I subtracted f of x0 from both sides to get this as being the same thing. So this claim is continuity, and it's the same as this question here, this issue here. Last question.
How did we get the 0 from x minus x0?
How did we get the 0 from this? So the claim that's being made, so the claim is y is this tending to that. So for example, I'm going to have to erase something to explain that. So the claim is that the limit as x goes to x0 of x minus x0 is equal to 0. That's what I'm claiming. Okay? Does that answer your question? Okay. All right. Ask me other stuff after lecture.